Good morning, everybody. Welcome to PyCon JP 2025. This is our first session here in Dahlia 2 today. And we will hear from Neeraj and Hitesh about dress code, how Python writes the future of fashion. So give them a warm welcome, please.
Good morning. So this is dress code, how Python writes the future of fashion. So whenever we hear the word Python, we mostly associate it with like AI applications, data science, building backend applications, and so on. So we just wanted to add another layer of like what all other applications we can just like work on, where things are just like expanding while you're currently working with your own domains, be it like AI models or data science. So to quickly go through the agenda, we're gonna start with computational design. What is it? How is it working? Where is it being used in the architecture space to fashion? We're going to draw the attention towards the fashion and then draw something on the fashion trends, where exactly things are happening. We're going to talk about a few algorithms, which we believe is like the most crucial one initially for 2D and 3D. And then once we are done with those, we'll just like see how we can fabricate those outputs in 3D and 2D on the form of like fabric design, laser cuts, and 3D prints. And if we get time, we'll definitely do some FAQ at the end of the talk. So this is a very simple map of where exactly we are sitting right now of Hiroshima. And I just wanted to show you this, like even a very simple map can be converted into a design which you can just like wear at your everyday life. So this is a small map which converted into a prettified version using OSMNX, which fetches those data. This is not created by me. This is created by some dude on the internet on Streamlit. And you can just like print it out, get up on the t-shirts. And by the way, this shirt, we just like printed it by creating our own design, which I'm wearing. So we're gonna see like how we can also create those like custom designs and just like work with it. So to begin with, we have computational design. So this is exactly where Python shines and merges those algorithms and aesthetics. So we'll see like how we define those numbers, do the maths, create those algorithms, and trace like everything on your fabric or the textiles. So computational design is pretty simple. You write some maths, you write some code, crunches it into the binary operations, and then it's just like rendered into a output. For instance, we have rendered a 3D twisted form of a pillar, which you can use in the architectural space. And while we're talking about architecture, this is an example of Nansha Sports Complex by Zaha Hadid Architects. And we wanted to show you this specific piece because generative design is drawing attention from all spaces, including a lot like dependence on generating algorithms, which is basically mimicking on how natural selection can be varied across disciplines. And what we are mostly doing in genetic algorithms is predefining those fitness functions and putting those constraints in the population by what maximizes the strength, what can take those load onto the pillars and all those aspects, and the environmental aspects as well. And whichever wins in the end, whatever the fittest works, and you can then work with it like as an actual building. So similarly in the fashion industry, we have like majorly two kinds of categorization. One is the parametric customizations. It can be the shapes which works on the basis of your body shapes, the way your body is performing. One of the examples we'll be seeing is like how we can simulate those heartbeat operations into a wearable outfit. And the generative textiles, one of which I'm currently wearing as well, where you can just like create those outfits, put it on a piece of textile, print it out, create those laser cut operations, which you'll again see in the later examples as well. And this is a very quick, like a history of evolution of how this industry have just like rapidly grown. 1960s, Ivan Sutlin's Sketchpad came into the picture. Everyone was so excited, like, okay, we have some computers to create those designs. 80s was all about like fractals, spins, and everything was working. Mandelbrot's and generative art came into the picture. Early 2000s was all about parametric tools. You have Grasshopper, Photoshop, and all the GANs again came into the picture in the mid of 2010s. And in 2015, it's all about AI-driven personalization. We can now beat the possibilities which were not possible previously. So that brings us to generative art. So in simple terms, anything which is created autonomously but which is not totally random, is generative art. So we don't want something which is a total chaos. We don't need something which is totally boring. We need something which is called effective complexity, which we'll see in a minute. And that's exactly just like shows you. So on the left-hand side, this is a piece which exactly draws those things. We are using a grid system by interpolating those colors from top to bottom. And those grids are also randomized. So we have a varied thickness and the width of those things. And overall, this art piece can be created. So this is something I got inspired by an artist called Felipe Pintone. So they create like all these like art pieces which they put on the museums, on the billboards and all those things. And yeah, so also it builds on rules. So we don't want to create something which is totally done by a system. So there needs to be a control, but it also requires a lot of randomness. And fractals are like one of the great examples which are quite simple, but like they do a really good job. We have like Pearl and Noise, which you also see, which works with the natural textures, Conway Game of Life, and so on. Then this is exactly what you want when you're working with an art piece. We don't want something which is like a symmetry or the tiling, a very simple structure. We don't need something which on the right side of the balance graph, which is like a chaotic system, a total randomization. What you want sits in the peak, like in the middle, which is the evolutionary system. And this is exactly which we'll see like how we can create those systems today. These are a few of the prints we created. Number one is a replica of like how Piet-Mondrian experiments work. Then we have the fluid simulations. This is one of the examples which you'll see in the next few slides, how Perlin noise can be simulated along with the physics simulations, which can push and make those like wave kind of structures. We have another wave fluid operations on the right-hand side. Oh, sorry. On the right-hand side, which again works with curve vertices and everything, and just like again physics has been simulated. So you're just like pushing a wind, and those things, the curve vertices are moving upwards. And we have the pixel sorting algorithm. This is again inspired by how sand moves when water waves comes into the picture. We're taking those pixels, pushing them towards like one way, as if the wind is just like coming from the other. So here we see an example from a very famous painting in Japanese culture, like how waves are being going. And this is what we try to simulate. Like you can create everything now using Python. So what exactly we're doing is also one thing, like we won't be able to show you like every single specific piece of code, like what we have written. We're just gonna go through the algorithms, like what's the main thing, which is like making them. And at the end of the presentation, we have a QR code. You can just like go and just like check the entire code pieces and just like play around with it. So what we're doing is we are first making the time fall off, which is like we want to make sure like it decays at a point. We don't want to just like keep it going until forever. We create those wave sizes. Again, we are just like reducing them one by one based on the time fall off. So that like the bigger waves goes on the top, smaller one goes below them. And then we are iterating over each wave. We're converting the x coordinate to oscillate between the minus wave by 2 position to the wave by 2, so that like we have a canvas ready for us. We do a deformation. So what you're gonna do is like we calculate those rotation angles, because when you see the waves, you need to make sure like they're not completely going under. They should stay over there. So we have a maximum bend, which is 1, and at the wave center, and then we have a 0 bend, which is at the edges, which means like it's stronger at the center and fades away when it goes towards the edges. Then we have a small modulation, so that like there is like a depth you can see on the wave, so that like it doesn't look like you have just like created like a sketch with like 5 different lines. So you can see those depths over there. Then we have a very simple rotation matrix over here. So new A, as you see, it takes the original x, the coordinate, the parameters, and then adds the change, which is A. And after one rotation is complete, and second thing, this is not a static image. It's basically a moving image. We just like took a snapshot and just like put it up on the previous slide. But this entire thing keeps moving. But like if you just like change a small parameter, change the random seed, you can generate a new kind of wave, and you have your own unique painting, I would say, or an outfit. So, and eventually we just like downscaling the size by 62%, so that like all the new waves goes below the previous one, and we get those like wave kind of structure. And that brings us to the second thing, which is the fashion trends, where Hitesh is just gonna give you an overview and show you some sort of examples like how actually fashion trends are going, and then we'll see some really good examples in terms of algorithms, and we'll see like how we are fabricating them into 3D now.
Yeah, thank you. Now that Neeraj has introduced computational design and evolution of fashion over time, we will, in this section, we'll explore something little more interesting. So we'll look at how AI Python is transforming fashion. Yeah, so one of the major disruption that's happening in the fashion industry is moving from waste heavy to zero waste manufacturing. So traditionally, production of fabrics and clothes has been waste heavy. So using technology and with advancement of technology, we are now moving towards zero waste manufacturing using algorithmic knitwears. So traditionally, fashion, like I said, fashion production has been waste heavy. What I mean by this is in the traditional processes, production starts with creating design as the first step. Once you have created the designs, you map those designs onto fabric sheets. And then you cut those designs, stitch the fabric, and create the final piece of cloth. Now, wherever the process of cutting is involved, there is wastage that is going to happen. So to eliminate these wastage and move towards zero waste, we need to completely eliminate the process of cutting. To give an example, say you buy 10 meter of highly expensive silk, and you buy a highly expensive silk and you want to design a sleeve. Now in the traditional process, you will first create the design, map it onto this silk fabric, and then stitch and prepare the sleeve. But like I said, the cutting process leaves a leftover. This will have both economical impact and environmental impact as well. To tackle this, the industry is moving towards zero waste production. So what we do here is, unlike the traditional process, like I said, we completely eliminate the cutting of designs. Basically, on the one side, you have a system of creating the designs, and on the other side, you have these 3D printers, which will take these designs and directly start knitting. So you don't have to map these designs onto fabric and cut. Now, between these two systems, that is creating the designs and printing those designs, you need a bridge to communicate. Python provides that bridge. Python provides libraries using which you can quickly prototype, innovate, and bring your ideas into reality. So this is one such example. Knitout is a Python library using which you can define on a very granular level exactly how the production of design should take place. So in this code snippet, you could see we first set up the printer parameters like the number of row needles. And then you could see there are two loops. So what we're doing is we're taking the needles and we are moving one needles forward in one step and one needle backward in one step. So that is going to create a zigzag pattern. So this is just one such example. You could have any ideas of producing a design, and you could use Knitout library to prototype. Next, another interesting trend is algorithmic textiles and smart fabrics. So traditionally, the clothes that you wear, the fabric piece has been static. And by this, I mean, the fabric does not react to your internal factors or external factors like movement, heat, temperature, etc. Designers and fashion producers are now slowly moving away from static to producing dynamic fabrics. Dynamic fabrics are those fabrics which respond to, say, for example, change in temperature. So the invention here is basically embedding of sensors into fabric that sends data to your systems. You may write simple Python programs and scripts which can read the sensor data and take actions according to the change. So for example, say you wear a nice fabric, but as you travel, the temperature of the fabric, the temperature of your surrounding might change. Say it goes from 25 to 35 degrees Celsius. This is detected by your sensor. The data is sent back to your system. The Python program then takes the action of basically flipping open ventilation in certain areas like your underarm, neck, and may also expand meshes to allow airflow in and out. So basically, we are using technology and especially Python to create programs that helps build dynamic fabrics. So this is just a simple code snippet to illustrate how this can be done. Third, and one of the most interesting, my personal favorite trend that I see is blending of modern fashion wear with old cultural and traditional touch to it. So fashion is one such space where things keep evolving, keep changing very frequently. Designers are using generative AI now to add cultural and heritage element to this ever-changing space. For example, imagine wearing just a modern hoodie, just a modern plain street style hoodie versus wearing a hoodie that has some cultural touch to it. You're blending modern style with some old heritage and cultural elements. So in this example, pardon me if I pronounce this wrong. In this example, we have taken kimono designs, which are Japanese inspired designs, and we are blending this with modern fashion like hoodies and shoes. So how do we achieve this in a very, very high level? We are basically using diffusers algorithms for this. You can use PyTorch, Hugging Face in Python to just quickly start and iterate over. So in this code snippet, we load a pre-trained diffuser model, and then we fine-tune on kimono dataset images. So we have kimono dataset with various styles. So we just fine-tune on this dataset. The end result is a trained model that has learned various things about kimono style. Once you have this trained model, you can use this model to output kimono-styled modern fashion based on a prompt or instruction that you give. Yeah, so you want to take over?
Yeah. So that took a lot of time. So let's quickly go with like some of the algorithms. We can see like these algorithms are mostly going to be fabric printed or the laser ones, like laser cut ones. And so they're like two traditional way of like creating those like generative art related outfits. Like one of the way is like you have match space operations for patterns and optimizations like waves, noise functions, and so on. And the second one are the AI based one, which they just like showed you like how you can diffuse those different art pieces and just like collate into a newer way of just like showing into your art pieces. Again, all these like code bases will be available eventually. So this is a very interesting example because everyone knows like how sine waves work. So, but what if we use a similar sine wave which computes an angle and which basically returns a value between -1 and 1. And what you're doing is like we take those the same principle and start creating those petals. So how exactly we're doing is if you look up on this thing, it's not the entire code for the entire petals, but just like giving you the gist of like how's it working. We first do the edge wave variation. So what you're doing is like we want to create those wavy organic wave. We don't want to create like a petal which is like a very harsh, rigid kind of a structure. So we just like create a sine wave and we just like pass those parameters. We know how much is the radius, what's going to be frequency. Frequencies basically denote like how wavy is the petal going to be. Then we also have the amplitude, which is going to be how far the waves should stick out of the entire flower, you can say. Then we have the size modulations. You can say we again create those sine functions so that like we want to make those petals breathe. So every next iteration should not be the exact same replica of things we're working. And again, this image is also a moving image. So petals can start growing and just like start moving. Then we calculate those positions at where exactly those petals needs to be created. We are basically converting those polar coordinates on the 2D Cartesian plane with varied wave distribution. And at the end, we are just like adding those surface texture, like how coarse, how color change it's going to be. So if you'll see here, so this specific piece shows how this specific art form has been created. But if you change those sine functions and add it to the curve vertex functions, which is if you are used to using libraries like processing, you can simply call them and just pass those parameters, and you will, instead of getting those very simple, smaller circular patterns, you will have those like squeaky patterns coming on. Then it comes the Perlin noise. So Perlin noise has been a very old concept since 90s, 83 3 or something by Ken Perlin, initially worked as a Tron movie example. And what we're doing here is like, we're saying Perlin noise is simply a random number. Just the random number has been associated with the chaos system. But here what you're saying is like, there is a, semblance between the last number generated. So if you generate a random number between 1 and 2, it's going to be random every single time. But here, it's going to be more of a coherent solution, so that like it knows. You can think of it as a memory, so that like Perlin noise functions knows like what was the last number generated. So instead of like, if you plot those random numbers on a 2D Cartesian plane, they'll just like look like a zigzag puzzle. But if you just like do the opposite and use a noise 2D functions or a noise function, that's not going to be like a zigzag thing. It's going to be more like a smooth circular wave going on. And that's exactly what you've done. We have just like plot those points on the grid systems, started them moving like in a specific plane. Maybe you can do on a plane mode, you just like add some more pixel sorting algorithm, just like push them across, and we played some colors and textures. So we don't have a lot of time, but like, I'll still give you like a gist of like how this sampling of noise functions are being worked around to make that specific piece of art, which you can eventually print it out on a texture, on a textile fabric, and just like put it as a t-shirt. So we have a base texture. We are sampling the Perlin noise with a frequency of 0.5 to get a larger pattern. Similarly, for the medium and fine tunes, we just like reduce them. Then we have the organic flow, organic wave generation, like how the wave's gonna be at the angle of like 360 degree. So because we want to make sure like those the flow fields are going from an angle of 0 to a 360 degree, but not so drastically. It's going to change like at a feasible rate. And then we are just like blending those rate, like how we want to blend those colors, because we have plotted like those contours kind of stuff, but we also want to play with the colors, like how those colors going to be blended across. We don't want to use any tool like lerp. We don't want to interpolate between a -1 and 1 value, because that's going to be too simple. We just want to make sure like things are flowing in a way it looks different than a normal gradient. So that's why we're just like adding those hue base, and we're remapping those layers with weights and the color selection, and we just like add the colors to the contours, and we get something like this. It's a simple single program. Every time you run it, you change the seed value. You have like hundreds and thousands of different variations. Last thing is algorithms is the fractals. Very simple. As in, the more you zoom in, the more outputs you're gonna see. As an SS, it's basically a complex plane, like X and Y. X is your real value, Y is your imaginary part. And so pretty simple, but yet very intricate outputs can be seen out of it. We are iterating again on a scale of 1 to 100. We are combining those circular sine functions over here, and with the exponential cos h functions. And for the v values, we're gonna be using the perpendicular wave patterns, so that like so it depends, like, so there are like 3 different outputs, so that the code I'm just like telling you specifically for the first one, the second and third one are created in the different manners. So your U and V values will just like differ accordingly. And then we are just like adding the real transformation part on the new X, so that like, the values are now changing. And then we're just like transforming the imaginary part with the values which you just like generated as U and V. We just like add those things, check left, like it's exploding out of 50. So that's where we know like it's done, because it's a very simple canvas. We don't have that computational part. If you have, you can just like go on. And eventually you will have those fractals, which you can just like keep zooming in. They will be a never-ending loop. So that brings us to the fabrication part. That's going to be the last set of this thing. And I think Hitesh can quickly go over like a few things. Then we'll see like how those origami structures can be printed out, and how we use like heartbeat simulations to create bracelets, and how we just like created our own algorithms to create your random hats you can wear every day.
Yeah. I think we just have 5 minutes left, so I'll quickly skip to the interesting part and get back to this if time permits. Yeah. So in this particular section, we are going to explore something very interesting. Now, creating a fashion object always starts with creating designs, and creating designs requires peak creativity. Now, designers usually seek inspirations from their surrounding, from their nature, but nature does not always give you what you need. So, with the use of technology, what we're doing now is instead of seeking inspiration from the nature, we can now seek inspiration from data. Today we have so much data, literally data about anything and everything, be it social data, be it economic data, be it hard data, any data that you speak about. And at the end of the day, all this data are just numbers. So the idea here is, how about you create a fashion design purely out of these data and numbers, which may represent anything. For this demonstration purpose, we have chosen heartbeat data, which I know is a little weird because it's not related to fashion, but that's exactly why we chose it, to show the capability that using any kind of data, you can create any fashionable object. So here in this small demonstration, we used heartbeat data to create a 3D bracelet. So on a high level, this involves 3 stages. One is creating the data, simulating your heartbeat data. Once you have that, you have the code to create the bracelet, and the last part is your visualization in 3D space. So to generate, I would just quickly glance over this because we just have 4 minutes left. To generate heartbeat data, we first need to generate RR interval. RR interval is basically duration between 2 heartbeats. So in an ideal world, every second you would have an heartbeat giving you 60 beats per minute. But in reality, due to various factors like emotions, stress, and various other irregularities, your RR interval will be uneven. So in this snippet, we have taken base heart rate, and to this we have added the irregularity based on emotional effects, where you can see we have captured the parameters like calm, excited, anxious, related, and we have added HRV factors. Basically, we are creating an equation where we are adding weights of these factors to generate this interval. Once you have the RR interval, we are going to generate 2 one-dimensional arrays, which is your T and signal. These are basically timestamp array and the signal array. You can think of it as an ECG graph, where the T array will represent the timestamp and signal will represent at what timestamp was the heart's electrical activity. Once we have this data, so basically right now we have 2 one-dimensional data, which is your timestamp data and your signal data. Now what we do is, our objective is to create 3D bracelet. So imagine you have this 1D line. What we're going to do is we're going to bend this 1D line to create a circle. And to bend this one-dimensional data into a circular data, you could see we have a code snippet there, the third one. So that is a code snippet that is going to bend this 1D line into circle. Once we have bent this 1D line into circle, what we do is we will use this signals array, which represents the heartbeat at a given point of time, to define thickness of the bracelet. So wherever there is a heartbeat, there is going to be some thickness defined by the amplitude of the heartbeat. So when there is a spike in your heartbeat, bracelet is going to have high thickness and spikes outwards. When there is low heartbeat, it's going to nudge inwards. So in a way, it's going to respond to your heartbeat. So this is the final outcome. I would personally not wear this bracelet. I know it's ugly, but for the demonstration purposes, the one towards your left is the raw output, where you could see there are spikes. Those spikes are basically representing your spikes in heart's electrical activity. Once you have those raw output, you could smoothen it out and you get this. And you can add designs using various algorithms that Neeraj explained to create more beautiful bracelet. We just have 1 minute left. So this is another demonstration where we are generating 3D hat using plain numbers and nothing else. And again, using plain Python. So this is basic flow where we take various parameters like cap style, pattern, package type, head count, head circumference, head radius, etc. Then we generate solid cap, we add patterns to it, we add comfortably factor to it, and we generate final output. So in the interest of time, I'm just going to skip over the code part. This is available in GitHub. You can download the repo, play around with it. I would just like to show the final output. Yeah, so this is the output that you get. So the idea of this demonstration is to show that using Python as a tool And using just plain numbers, any kind of data and plain numbers, you could create fashionable objects. So yeah. Thank you.
Thank you so much. And if you have some questions, I think we can take those questions outside after this. And if you go to this QR code, you will go to the GitHub. You have the presentation slides. You have all the code files. You can just check them out. Thank you.
Yeah, thank you very much.